So, the plan is to give, for this talk and for the next couple of talks, to give a brief sort of self-contained introduction to the ideas of PT-Symmetric quantum mechanics, which is an idea that's actually goes back to to about 1988 and the work of Carl Bender, who at the time I think was at Imperial. He's now at Washington, I think. Although the field's been around for about 20 years, it's really only gotten teeth in the last couple of years, and the plan is to kind of give a summary of, in particular, some ideas that have emerged only in the last year or so, primarily from Carl Bender himself, Dorkay Brody, and Marcus Muller, and also some things that are currently being worked on by me and a couple of other people. So PT-Symmetric quantum mechanics is a kind of a novel interpretation of QM that relaxes some of the standard mathematical axioms of quantum mechanics. And although today I'll mostly focus on just kind of the underlying algebra and mathematical structure of the theory, the plan for the next couple of talks is to give some examples of how it can be applied to make explicit connections between quantum mechanics and analytic number theory. And that will culminate in the, we'll explicitly construct a Hamiltonian with the property that its eigenvalues are exactly the imaginary parts of the non-trivial zeros of the Riemann zeta function, so that effectively you can reduce the Riemann hypothesis to a claim about that a claim that a particular quantum mechanical PT-symmetric Hamiltonian is manifestly self-adjoint. But that will come later. There's quite a lot of kind of analytic machinery that has to be built up before we can do that. Okay, so before I can say anything about PT-symmetric quantum mechanics, let me first say something about regular quantum mechanics. So the mathematical formalism that goes back to people like John von Neumann and Eugene Wigner and Paul Dirac relied upon a set of assumptions about Hilbert space. So the idea is that your space of quantum states is a Hilbert space, so it's a vector space, usually complex, usually infinite dimensional, that has an inner product that's defined on it and which is complete in the sense that limits can be defined at every point. And so then that Hilbert space is spanned by some orthonormal set of quantum basis states, so that any arbitrary quantum state is a linear superposition of the basis states. In other words, it's given by some complex linear combination of the basis states, and then if you perform a measurement on that state, the probability of measuring it in any one of those basis states is given by the complex coefficients are referred to as probability amplitudes, and the probability of measuring it in any given state is computed by taking the probability amplitude, taking its absolute value, and squaring it. And so then the Hilbert space gives you the sort of the mathematical structure of your quantum of your space of quantum states. Then any physical observable is treated as an operator that acts on that Hilbert space. So and the standard. So okay, I've already mentioned kind of one of the standard mathematical requirements, which is the set of your basis states ket En is orthonormal. Relatedly, we assume that the operators that act on that space, which correspond to the physical observables, are Hermitian. So, for instance, something like that, the Hamiltonian operator that characterizes the total energy of a quantum system should be Hermitian, so that h hat adjoint is equal to h hat. And the rationale for imposing this condition, well, there are several, but so one of them is that it ensures that, of course, all of your operators have real eigenvalues, and given that when you make an observation, the outcome of that observation is given by a linear combination of the eigenvalues. It ensures that whenever you measure some physical observable, you always get a real number out, because if your observables are physical, they damn well better correspond to real numbers. The other thing is that because the eigenvalues are real numbers, when you perform this probabilistic interpretation by taking the amplitudes and taking the absolute values and squaring them, you always get non-negative numbers, because again, negative probabilities are usually a sign of a bad theory. And then the other rationale is related to the third of the axioms that I want to discuss, which is to do with time evolution. So we define the time evolution operator u hat is some function of time, which we can define to be e to the minus I h hat t over h bar, where h bar is just a reduced point constant, which we'll use God's units, so that h bar is equal to 1. And so then if h hat is a Hermitian operator, this ensures that u hat, so u hat, as I say, time corresponds to the time evolution operator, so you apply this to some quantum state for some positive value of t, and it tells you what the quantum state will be at some point in the future. And in particular, you want the time evolution of the quantum state to be exactly reversible, so you don't want the system to be losing any kind of information with time. And so this turns out to be related to a unitarity condition. So in particular, if h hat is Hermitian, it ensures that u hat is a unitary operator, so that u hat adjoint u hat is the identity. That enforces the condition that when you perform a probabilistic interpretation and you sum over all quantum states, the probability is always summed to 1, because effectively if they summed to less than 1, you'd be losing information with time in some sense, and that would prevent the evolution of the wave function from being exactly reversible. So yet another justification for wanting hermiticity of your operators is to ensure that time evolution, when defined in this sense, is unitary, and you get exact reversibility of quantum evolution. So the idea, as I say, that goes back to Carl Bender, that's really quite remarkable when you start to think about it, is that you can take the standard mathematical structure that was imposed by people like Dirac and basically just screw all of the standard axioms and still obtain a perfectly self-consistent interpretation of quantum mechanics. Now that's extremely non-obvious, and and the reason why it wasn't realized by people like Dirac is that it only becomes clear if you adopt a very particular mathematical formalism called biorthogonality. So let me now say something about biorthogonality. So this is an idea that comes from multilinear algebra. So if we have a pair of topological vector spaces, E and F, that are in duality, and we have a pair of indexed families of vectors, which I'll denote UI in E and VI.
What does it mean for them to be in duality?
Well, in our particular case, all that matters is that they're equidimensional.
Okay.
But there is a more formal definition, but it doesn't actually matter for the biorthogonality case. And we assume that both vector spaces are equipped with some bilinear mapping that I shall interpret as an inner product. And we say that this pair of indexed families is biorthogonal if and only if the inner product of UI with Vj is equal to the Kronecker delta of I comma j. So I think this is actually kind of bad notation, because it seems to me that this should be bi-orthonormality and that biorthogonality should mean there's some constant of proportionality there. But anyway, I'm not an algebraist, so don't ask me. So then the kind of the broad scheme with PT-Symmetric QM is that you relax the requirement that your basis states are orthonormal. You just start with some random, like, linearly independent set. And so you start with a Hilbert space in which your operators are not Hermitian, in which time evolution is not unitary. And through biorthogonality, you construct a second Hilbert space that is physical, in which the standard requirements of quantum mechanics are satisfied. And the key insight from Brody came from the fact that in order to have kind of physical consistency, all that matters is that the quantum state be parity time symmetric, i.e. PT-symmetric. So let me just make a quick sort of philosophical point that it's conjectured that the fundamental symmetry of our universe is CPT symmetry. So C stands for charge, P for parity, T for time. So we know that any one of these symmetries, and indeed any pair of these symmetries, can be violated. But the current conjecture in particle physics is that the triplet is inviolable. So in other words, if I take you and I put you in a universe where all the charges are reversed, so every positive charge becomes negative, every negative charge becomes positive. Parity is reversed, so all the kind of chiralities are flipped from being left-handed to right-handed or whatever. And time is flipped, so instead of flowing from past to future, it flows from future to past. The conjecture of CPT symmetry is there is no way in principle for you to determine that I've done that the universe you inhabit will be indistinguishable from our current universe. And so for the foundational structure of quantum mechanics, charge doesn't really matter. And so the realization of Brody was that all that really matters if we want to get a consistent interpretation is that it be PT-symmetric. And so all that we really have to show is that if we start by relaxing these assumptions, we can still construct an interpretation of QM where which is invariant, where the quantum state is invariant under parity time reflection or space-time reflection. And so what we do is, using biorthogonality, we construct this physical Hilbert space in which our operators are no longer Hermitian, where our time evolution is no longer unitary, but where we still get reality of physical observables, real eigenvalues of our operators, and in which there's a way you can define the time evolution operator such that although it's not algebraically unitary in the original state space, you still get a kind of physical unitarity in the sense that the quantum state is the time evolution of the quantum state is still exactly reversible. And that's kind of what I want to prove for today's lecture, and then later on, whenever the next talk is, I'll sort of make this connection with analytic number theory, which is a little bit more complicated to explain.
A question on the philosophical point. Sorry.
Yes.
You mentioned the conjecture is that the CPT symmetry cannot be violated, but any pair can be. Mm-hmm. So does that mean the PT pair can be? Does that cause problems? Or...
It doesn't, no, because so the point is that the mathematical formalism of quantum mechanics is kind of insufficient for describing the whole universe. You need quantum fields, you need gravity, other kinds of stuff. The point is, if we lived in a universe that was only quantum mechanical, because everything I'm going to discuss now doesn't involve charge, then all we have is just kind of pure PT symmetry. The point is that once you bring charge in, then PT symmetry it's possible to violate. So,
Okay, so as long as we ignore charge, there's not problems.
Yeah, exactly. So,
Okay.
I mean, we know that once you bring in other parts of physics, parity symmetry we can violate quite easily because, there are like electrons where if they're left chiral and you put them through a graphene lattice, they scatter differently to right chiral electrons. And time symmetry you can violate, for instance, by having, if you have a meson, like you have a pair of quarks and they're kind of, they're oscillating, the pattern of the oscillation is not time symmetric. So you could, in principle, work out by looking at meson oscillation whether you're seeing something being played forwards or backwards. And then again, there are things. If you couple parity and time, there are still physical experiments you could do to determine that. But the point is, those experiments would not be doable if you were in a universe that was only described by quantum mechanics.
Okay.
But that's a good thing to clarify. Okay. Destroy the whiteboard.
I have 2 more. So.
Oh yeah, true.
Do you need someone to hold the other end of that while you're doing it, or?
I think we're okay. But it's hard to tell. Okay, anyway, let me now actually describe how we construct this physical Hilbert space that makes everything sort of work. So we start with some linearly independent set of basis states, so ket phi n, for n going from 1 to n. So we're implicitly defining some n-dimensional Hilbert space. So it's worth mentioning at this point that everything I'm going to be saying for the first part of the talk applies for finite dimensional Hilbert spaces only. And it's very reasonable to ask well, what about the sort of more physical infinite dimensional case? But the point is, and towards the end, I'll kind of discuss to an extent, or I'll discuss to what extent the methods of analysis that I'm going to apply in the first part of the talk extend to the sort of infinite dimensional case. But there are some mathematical subtleties there to do with boundedness of operators and so on that I kind of don't want to get embroiled in. So for now, let's just assume we're in a finite dimensional setting. So we start with this linearly independent set of basis vectors, and we're particularly interested in the case where these vectors are not orthonormal. So then what we do is, okay, so suppose we have some, let me not get ahead of myself. Suppose we have some ket phi k. We use the notation ket chi k to denote an element of a one-dimensional subspace of our Hilbert space that is orthogonal to the span of the set ket phi n for all n not equal to k. And so in that way, we implicitly define a biorthogonal pair, or a pair of biorthogonal families, such that the inner product of phi n with chi m is proportional to the Kronecker delta of n comma n. And in fact, in just a moment, we're going to set some normalization convention that puts this constant of proportionality to 1. So then what we can do is, because by assumption our original set of basis states was linearly independent, we can take some arbitrary quantum state, ket psi, and expand it uniquely as a sum over n of Cn ket phi n for some complex numbers, some probability amplitude Cn. And then we can denote an associated state, ket psi tilde. So the notion of an associated state occurs kind of quite naturally in the study of real Hilbert spaces, but we're going to use it here for a very specific purpose, which is we write the associated state as the sum over n of Cn ket chi n. So in other words, it has the same probability amplitudes, but instead we're using the biorthogonal basis rather than the original basis. And so our motivation for introducing the associated state is that we can then define the physical Hilbert space in accordance with the following scheme. So we start with a pair of quantum states. So ket psi is sum over n of Cn ket phi n, and ket phi, I will let that be the sum over n dn ket phi n. And then, so we define our physical Hilbert space by the scheme that the inner product in this new space of phi with psi is defined to be the inner product with respect to the original Hilbert space of the associated state phi tilde with psi, which we can just expand out as a sum over all n and m of dn conjugate cm times the inner product of chi n with phi m. And as I mentioned earlier, I'm now just going to implicitly adopt the normalization convention so that the inner product of chi n with phi m is identically equal to the Kronecker delta function of n comma m. So now this inner product just reduces to a Kronecker delta, which we can now use that to eliminate one of these sums because all of the off-diagonal elements disappear. And so this just becomes the sum over n of dn conjugate cn. And so now we have a scheme for constructing a new inner product space that I claim is now a physical Hilbert space. So now let me discuss some of the implications of that. So we can now take we can imagine some operator of a generic type acting on a Hilbert space, which I'll call f hat. And so f hat is going to have some general form, which I shall now just double check. So we have f hat will be the sum over all nm of fnm, little fnm, times ket, let me get this right, ket phi n bra chi m, where fnm is just some arbitrary two-dimensional complex array. So crucially, this is not an operator on a Hilbert space. It's just some array. And the point is that we can see immediately that this, well, hang on. If we now consider the what the expectation value of this operator will be. So the expectation values, as in standard quantum mechanics, we can just compute by taking an inner product, computing the projection in the direction of measurement. So the expectation value is then just going to be whatever it is, brass psi tilde f hat ket psi normalized by the inner product psi tilde psi. So then, which we can, if we like, expand out as some sum of nm of psi tilde. So that's going to give us, hang on, what is that going to give us? Ket chi m. So that's going to give us dm cn, dm conjugate cn times f and n over sum over n of cn conjugate cn. So we can see immediately that the expectation values are going to be real if and only if this two-dimensional complex array fnm satisfies some pseudo-hermiticity condition where fmn conjugate is equal to fnm. So, in other words, if we were to interpret F as being a matrix, it would be a Hermitian matrix, but crucially it's not. It's not an operator on a Hilbert space, so we don't interpret it as a matrix. And the point is that this pseudo-hermiticity condition that's required for the reality of the expectation values can hold even in the generic case where F hat is not itself a Hermitian operator. Okay. So we're considering some... I should have mentioned this. We're considering the system prepared in some generic state. Yeah. This should have been obvious. Okay, what do I want to address next? Okay. Let me now talk about the probabilistic interpretation. So if we imagine that our quantum, let's now just enforce the fact that that the operator f hat has real eigenvalues, or has real expectation values, or in other words, let's enforce the fact that Fnm is pseudo-Hermitian, and let's consider a system prepared in this generic state we're considering, Cn ket phi n. And so we have our operator f hat, and let's now ask the question, and we're going to assume that it has eigenvalues fk, which by definition are real, and it has associated eigenstates, which I'll denote ket fk. And we can ask the question of, well, if we perform a measurement, or maybe I should call it fn, sorry, that would be a more consistent notation. But then we can ask the question of, if I perform a measurement on our observable f hat, what's the probability that the outcome of that measurement comes out as ket fk? Or the outcome of the measurement is the real number given by fk, and that's just as in standard quantum mechanics we compute by an inner product. That probability is going to be given by pk, where pk is going to be, let me work this out, that's going to be the inner product of fk tilde with psi times the inner product of psi tilde with fk, normalized by the inner product of psi tilde with psi times the inner product of fk tilde with fk. And so trivially, from the fact that all of these eigenvalues have to be real by definition, we can see just by the nature of inner products that Pn is going to be non-negative for any n. And by expanding out these inner products in summation form and then doing the kind of manipulation with biorthogonal states, which I'm not going to do because it's kind of horrible, but it's not too hard to convince yourself that the sum over n of Pn is in fact 1, and that this holds even in the more general case where the inner product of the where the actual eigenstates are not mutually orthogonal. So this holds in the generic case where the inner product of Fn and Fm is not equal to 0. And so therefore we can deduce that we get a perfectly consistent probabilistic interpretation of quantum measurement without us ever having to care what the actual values of the overlaps of Fn with Fm, which by definition are equal to the overlaps in the basis states phi n, phi n. We never actually have to care what these numbers are, and that's a theme that we will sort of continually return to, and it will become quite important for the proof towards the end. Okay, so that's a little bit about probabilities. Now let me say something about dynamics. So let's now imagine, rather than considering some arbitrary operator f hat, let's now actually consider a Hamiltonian operator for some quantum system characterizing the total energy. So, what I claim is that if we take H hat to be some non-Hermitian PT-Symmetric Hamiltonian, we take time evolution to be what it normally is, e to the minus I H hat t over H bar, then obviously we don't have unitarity in general, at least in the algebraic sense. But my claim is that one still obtains physical unitarity in the sense that however much one applies the time evolution operator to an initial quantum state, it is always possible in principle to reconstruct the initial quantum state from quantities that are physically observable. So let me now prove that. So we start by considering the time-dependent Schrödinger equation. So IH bar dt ket psi t is equal to k hat ket psi t for some arbitrary operator k hat. And so we consider a quantum system prepared in some generic state, some generic initial state, ket psi 0, is the sum over n. Oh, I should mention, of course, because this is PT-symmetric, we're assuming that we have entirely real eigenvalues En and associated eigenstate. And associated eigenstates that I'm going to denote ket phi n.
Can I ask, do the eigenstates necessarily span the space of states with a pseudo-Hermitian operator?
Yes, because they'll be linearly independent, just not orthonormal. which actually follows from the probabilistic argument I gave over here. So yes, so if we start with some generic initial state, sum over n of Cn ket phi n, which yes, because it's linearly independent, we can just assume is a basis as good as any other. Then we have some general. We consider some solution for some positive time. So ket psi t, we obtain this just by applying the time evolution operator to this initial state. So we get this is going to be the sum over n of Cn e to the minus I ent over h bar times ket psi n. I'm running out of chalk. So now, if we consider the conjugation relation that defined the associated states on our original Hilbert space. So just to recall, the conjugation relation for some generic state ket psi was given by ket psi tilde is the sum of n of Cn ket chi n, where ket chi n denotes the bi-orthogonal basis. So from this conjugation relation, we can now see that if we take this state and we perform an inner product of the following kind, we say that the inner product of the associated state psi t tilde with psi t, this is clearly because the reality of our eigenvalues ensures that this exponent is just going to be some kind of cyclic thing. So this ensures that this inner product is always going to be equal to the inner product of psi 0 tilde with psi 0. And in fact, more generally, if we have some different solution to the Schrödinger equation, phi t, for a quantum system prepared with some different initial condition, phi 0, we're going to have this general unitarity condition that for any t greater than 0, the inner product of the associated state phi t tilde with psi t is going to be equal to the inner product of the associated state phi 0 tilde with psi 0. So in other words, however much we apply the time evolution operator, however much we let the system evolve in time, it will always, in principle, from its current quantum state and from the bi-orthogonal basis, be possible to reconstruct what the original state of the system was. So in other words, even though we've relaxed the kind of algebraic unitarity requirement for our physical Hilberts, for our original state space, we still get unitarity in a physical sense in the space defined through bi-orthogonality, and we still get consistency of probabilistic interpretation. And that completes that proof. Okay, and now let me clear some more space. So as I mentioned earlier, what we've shown is that starting from these relaxed requirements, we still get reality of physical observables, still get consistency of probabilistic measurement, and we still get unitarity of physical unitarity of time evolution. And critically, we've been able to prove all of these properties without us ever actually knowing what the overlaps between the basis states were. So in other words, we never had to care what the actual numerical values of this inner product, phi n with phi m, actually were. And so from that, because we've been dealing only with kind of physical observables, it's tempting to conjecture that these numerical values should not themselves be physically observable. And in fact, that turns out to be the case. So it's a theorem that the numerical values of this inner product, not only are they not physically observable, they also can't be estimated from any measurement that you could in principle perform in a closed quantum system. And so let me now prove that. So I'm going to do this proof in two parts, because there is an original proof based on ideas due to Brody. The problem is that proof is kind of abstract and a bit, I don't know, if you're anything like me, I'll just talk through the proof, but I say, if you're anything like me, you won't find it particularly convincing or satisfying. It doesn't really provide any illumination. So then I'll give the general proof for the n-dimensional case, and then I'll give an illustrative proof of how I'll give an illustrative example of how the logic of the proof works for a sort of representative two-level quantum system that I think is much more, gives you much better intuition as to what's actually going on. So the essential idea is that you're given a bi-orthogonal basis. You're given a basis, ket phi n, and bi-orthogonal partner states ket chi n. And then you can what you can do is construct the algebra of all physical observables explicitly without referring to any other components. So then, by definition, or by construction, any observable of your quantum system is then given by, up to a trace, a linear combination of the elements of that algebra. And then the elements of the algebra, although those elements themselves depend upon the inner product of phi n with phi m, because as we've shown earlier, sorry, I've erased it now, but as we showed earlier, the expectation values of your physical observables depend only upon the original state, ket psi, and on the expansion coefficients of the observable in terms of the elements of the algebra, it follows that the actual numerical values of phi n and phi m cannot be estimated from any observation that you could perform within the closed quantum system. So that's the kind of broad abstract proof, but it's not a particularly satisfying thing. So let's do a particular example, so proof for a two-level system. So in other words, we start with some pair of orthonormal states, ket E1, ket E2, and so now we prepare some arbitrary linearly independent basis. So of course, without loss of generality, one thing we could do is just say ket phi 1 is proportional to ket E1, and I don't know, ket phi 2 is proportional to whatever it would be, cosine, like 1/2 zeta ket E1 plus sine 1/2 zeta e to the I eta ket E2. Okay, that's one thing we could do. But I'm actually not going to do that, because what I want to do is make the elements of the algebra of observables that we're going to construct a little bit more symmetric, so it's slightly nicer to reason about. So instead, I'm going to construct our arbitrary biorthogonal basis using a slightly more complicated scheme, whose coefficients I hope I can remember. But if I can't remember them, then it'll be fun trying to reconstruct them. So we'll construct it by the scheme ket phi 1 is 1 over the square root of 2 sine 1/2 zeta times the cosine of 1/2 zeta plus sine of... Oh, I should mention, like, zeta and eta are just arbitrary parameters here, whose significance will become clear in a moment. So we have 1/2 zeta, cosine 1/2 zeta plus sine 1/2 zeta times ket E1 plus, let me get this right, cosine 1/2 zeta minus sine 1/2 zeta times e to the I eta ket E2. Okay, and then ket phi 2 is going to be given by the same kind of thing, but with slightly different coefficients. So it's going to have the same exterior coefficient, cosine, it's going to have the same cosine. This will instead be a minus. That'll be the same. This will be still a plus. This will be a plus, and that will be the same. And then to construct the biorthogonal partner states, ket chi 1 is going to be given by, so this will be the same, this will be the same, this will be now a plus, that will be the same, this will be a minus, that will be a minus, and then for ket, I'm running out of space here. And then for ket chi 2, it will go like, whatever, this will be the same, this will be the same, that will be a minus, that will be a minus, and that will be a plus. Okay, I hope that works. Something like that holds. Right, so that gives us our kind of arbitrary linearly independent but biorthogonal basis, or arbitrary linearly independent basis, ket phi 1, ket phi 2, and then it's biorthogonal, a set of biorthogonal partner states. Oh yeah, this should be minus that, I think. Anyway, so then the point is that in sort of a standard Hermitian PT-Symmetric quantum, in standard quantum mechanics, when you're dealing with a two-dimensional quantum system or a two-level quantum system, as those of you, as you should know, I think, because I believe it's in groups and symmetries somewhere, that any observable on a two-level quantum system is given by a linear combination of the three Pauli matrices, sigma x 0, 1, 1, 0, sigma y is 0, minus I, 0, and then sigma z is 1, 0, 0, minus 1. So then in this more general case where we're dealing with PT-symmetric but non-Hermitian operators, we can compute the Pauli matrices using this, directly using the algebraic definitions of ket phi 1, ket phi 2, ket chi 1, and ket chi 2, and that's going to give us a set of operators. Sigma x hat is 0, e to the minus I eta, e to the I eta 0. Sigma, let me do this on another line. Sigma y hat is going to be I times the cotangent of 1/2 zeta minus I times the cosecant of 1/2 zeta e to the minus I eta. Then this is going to be I times the cosecant of 1/2 zeta e to the I eta, and that's going to be minus I times the cotangent of 1/2 zeta, and I fear I'm going to have to make an abrupt color change. And so sigma z hat gets its own color, and that's going to be whatever it is. What is it? Oh yeah. Cosecant of 1/2 zeta, and then that's going to be minus the cotangent of 1/2 zeta e to the minus I eta. That's going to be the cotangent of 1/2 zeta e to the minus I eta, and that's going to be minus the cosecant, yes. And that will presumably work. And so then, as I mentioned, up to a trace, any observable that's acting on our non-Hermitian PT-symmetric quantum system will be given by some linear combination of these extended Pauli matrices. So it's worth noting actually that this is, up to unitarity, this is the most general set of the most general possible set of Pauli matrices, and these are in general not Hermitian. I think in this particular case sigma x hat is Hermitian, but the other two are not. And one recovers in the limit as zeta goes to pi, eta goes to 0, one recovers the standard Hermitian triplet. And it's not too difficult to verify that indeed the triplet sigma x hat, sigma y hat, sigma z hat transforms as an SU2 vector and indeed satisfies the standard little SU2, satisfies the standard commutation relations of the little SU2 Lie algebra, which is kind of what we want. So then, what we can do is, if you recall the formula we derived earlier for the expected value of some arbitrary observable f hat in some arbitrary state ket psi, which was given by bra psi tilde f hat ket psi normalized by the inner product of psi tilde with psi, then we can use this formula to compute what are the expected values of the three Pauli matrices, and I believe with some linear algebra one obtains. Somebody may want to check me on this, or not. Sigma x hat sine theta cosine phi. Oh, sorry, yeah. This is for some generic quantum, for a system prepared in some generic quantum state, ket psi given by cosine 1/2 zeta ket phi 1 plus sine 1/2 zeta e to the I. No, this is, sorry, 1/2, let me use different coefficients so it doesn't get confusing. Cosine 1/2 theta ket phi times plus sine 1/2 theta e to the I phi ket phi 2. So then this is going to be, this expected value is going to be sine theta cosine phi. Then the expected value of sigma y hat is going to be sine theta sine phi. And the expected value of sigma z hat will just be cosine theta. Okay, what did I want to say next? Let me try and give some semblance of structure to this. Okay, so the critical observation to make here is that these expected values are completely independent of the parameters that were the arbitrary parameters zeta and eta that we use to construct the algebra of observables. So, in other words, what we can do is we can take any arbitrary operator that acts on our Hilbert space, f hat, and expand it as time times the identity operator plus x times sigma x hat plus y times sigma y hat plus z times sigma z hat. And we can see that because any operator can be written in this form, and that all of these, the expected value of each of these elements, or each of the terms in this expansion, are independent of the arbitrary parameters zeta and eta, it follows that these two parameters cannot be observed or estimated from any measurement that we can apply in the system. And so this is a kind of concrete illustration of the abstract proof that I presented earlier. Okay. Are we okay so far?
Mm-hmm.
Right. So now, let's consider. Let me give a more explicit example of a kind of object of interest that, by this formalism, is unmeasurable within any closed quantum system, and that is the so-called metric operator, i.e., the operator that corresponds to the metric that acts on our original Hilbert space. I claim is not observable in any closed quantum system of this kind. So let's consider now a Hamiltonian written in accordance with this prescription. So H is prime times the identity times plus x times sigma x hat plus y times sigma y hat plus z times sigma z. Okay. Yes, fine. So before I move on to the metric operator case, there was just one kind of broader philosophical remark I wanted to make about the meaning of this proof. What this is essentially telling us is that we have some hypothetical experimenter, and they're manipulating some closed quantum system. The only parameters that they could, in principle, modify are those in the triplet x, y, z, or in certain conditions, t, but that they have no control over the parameters zeta and eta. One other philosophical remark that's kind of interesting is that this sextet of parameters, t, x, y, z, zeta, eta, corresponds to the minimal set of parameters that one needs to specify the most general 2x2 PT-Symmetric Hamiltonians. Okay, so then my claim is that the metric operator on the original Hilbert space is not an observable quantity. So to deduce that, let's start with our linearly independent basis set and its set of bi-orthogonal partners, ket phi n. And then let me define a pair of operators, u hat and v hat, by the following prescription. That u hat, let me get this right. So u hat applied, yeah, okay. So, and we also have some orthonormal basis, ket en. So then u hat applied to ket en is going to be ket phi n, and v hat applied to ket en is ket chi n, the bi-orthogonal partner state for any n. And as we shall see, some combination of these operators corresponds to a metric defined on our original Hilbert space, but that metric cannot be an observable quantity in this scheme. Let me just check that I got that right. Yes, I did. Okay. So in the particular two-dimensional case that we were considering earlier, we can immediately see that both of these operators, u hat and v hat, are completely determined by zeta and eta, because in effect they're going to be matrices given by the transpose of the matrices of coefficients that I've prescribed for ket phi 1, ket phi 2, ket chi 1, ket chi 2. So now what we can do is use the fact that our set of our original set of basis states ket phi n is linearly independent, which implies therefore that the operator u hat is inversible, and in fact its inverse is going to be given by v hat adjoint. So in other words, v hat adjoint u hat is going to be equal to the identity. And then from the orthonormality condition, in effect this follows from the fact that the inner product of chi n and phi n is delta nm. So now what we can do is make a formal substitution. So we say u hat, ket phi n we can substitute for u hat en, and because of this relation between v hat and u hat, we can also substitute the inverse of the Hermitian conjugate of u hat times ket en is going to be ket chi n. And we can make this formal substitution in the expansion of some arbitrary operator, the sum over n and m of fnm ket phi n bra chi m. So then this will give us, hopefully, a similarity transformation. Indeed, what it tells us is that f hat is going to be equal to u hat times little f hat times u hat inverse. Sorry, not adjoint. Where little f hat is just the sum over n m of what is this going to be? It's going to be the sum over n and m of f and m times ket en times bra en. Okay, so in other words, what we have is we have this Hermitian operator little f hat, which is now related to our generic non-Hermitian operator big F hat by a similarity transformation where where we're conjugating f hat by u hat. Okay. So, right, where are we? Yes. So this operator u hat is uniquely defined up to unitarity. Well, up to a unitary transformation that corresponds with the choice of orthonormal basis ket en. So now we can take the Hermitian adjoint of big F hat. And what are we going to obtain? We're going to obtain u hat adjoint inverse times f hat, because f hat is like invariant because we can see that this is a Hermitian operator, times u hat adjoint. But we also know that from this relationship that little f hat is going to be equal to u hat inverse times big F hat times u hat. So in other words, what we obtained is a further conjugation relation where f hat adjoint is going to be equal to u hat times u hat adjoint inverse times bigger hat times u hat adjoint. So this thing here, u hat adjoint, is a positive Hermitian operator that is inversible, and so it's worth making another kind of broader connection with the mathematical structure of quantum mechanics here. In finite dimensional Hilbert spaces, the standard mathematical structure of quantum mechanics is insufficient for for prescribing reality of observables and so on. What one has to do is effectively augment the Hilbert space with some additional structure, which is called the metric operator, which is really a positive Hermitian quadratic form of the type u hat times u hat adjoint inverse. And so, just to make a historical point, Dirac, when he was kind of setting up the mathematical formalism of quantum mechanics, made what is arguably kind of the most elegant and economical choice, which was just to set g hat, the metric operator, to be equal to the identity, which meant that QM had a fairly nice mathematical structure, but it had this unintended consequence of obscuring this stuff to do with bioorthogonality. So if you now let g hat, the metric operator, be some more general kind of thing, what we see is that the way we derive the adjoint of f hat is by conjugation with the metric operator. So what we can do, if I've got this right, is if we take our no, not the expected value, just the standard expansion of f hat, and we have some generic states. And then we can take f hat as wait, is this correct? Yeah, no, this is fine. So that's now going to be the expected value. Let me check that I'm not completely fucking this up. Yes, okay, so we are taking expected values here. So what we can exploit is the fact that v hat applied to ket en is equal to ket chi n, but then v hat we've already established is equal to u hat adjoint inverse applied to ket en, but then u hat adjoint appears in this relation here, so we get that this is actually equal to, what is this actually equal to? This is actually equal to u hat adjoint inverse times u hat inverse applied to ket phi n, but that is just g hat. So, in other words, we can derive we can derive ket chi n by applying the metric operator g hat to ket phi n. So to now convince you finally that this is indeed a metric operator on our Hilbert space, it suffices only to consider the expectation value of f hat when the system is prepared in generic state ket psi, which is going to be graph psi tilde f hat ket psi over the inner product of psi tilde with psi. But then we now have a scheme for deriving the associated state in terms of the original set of bases using the metric operator, or I shouldn't call it the metric operator, using g hat. So this is now going to give us bra psi times g hat f times cap psi over bra psi g hat cap psi. Which shows us that, in fact, yes, g hat indeed acts as a metric operator on our original Hilbert space. But so now we can observe that the free parameters that were involved in the definition of g hat are exactly the free parameters that were involved in the specification of the algebra of observables. So in the two-dimensional case, for instance, that would be the arbitrary pair of parameters zeta and eta, and it therefore follows that the g hat operator that acts as the metric on our original Hilbert space cannot be observed by the previous theorem. And that completes the proof. Okay, so that's pretty much all I wanted to say for today, just to kind of introduce you, give you a flavour of the mathematical structure of PT-Symmetric QM, try to convince you that even when you relax hermiticity, unitarity, and all of these kinds of things, you still get real observables, you get real eigenvalues, you get proper kind of unitarity of physical evolution. So let me just conclude by mentioning a few open problems that are currently being worked on. So I mentioned towards the start that everything I've talked about today really only applies in the case of finite dimensional Hilbert spaces for a very good reason, which is that the methods of analysis I've used have assumed that our bi-orthogonal basis set is complete. But the problem is that when one considers an infinite dimensional Hilbert space, even if you have a complete set of basis vectors ket phi n, the associated bi-orthogonal set ket chi n does not itself have to be complete, and that kind of screws most of the methods of analysis that I've used here. So, but what this sort of foregoing analysis does show is that even in both the finite and infinite dimensional case, a PT-symmetric Hamiltonian operator that is non-Hermitian, which also has PT-symmetric eigenvalues, is physically indistinguishable from a kind of associated Hermitian Hamiltonian or associated Hermitian operator. And in the finite dimensional case, we've shown that they're equivalent. In the infinite dimensional case, we've merely shown that they're physically indistinguishable. But it nevertheless leads one to, even though these methods of proof can't be extended naively into the infinite dimensional case, it leads one naturally to conjecture that if you have that any operator that admits PT-symmetric eigenvalues in the way that we've described should correspond to a perfectly reasonable Hamiltonian operator for some physical system. And in particular, the unboundedness of the metric operator G hat or its inverse, G hat inverse, should not have any physically observable quantities. That's still kind of unproven, but it's a sort of a natural implication of the methods of analysis that we've used here. So I'll stop for now, and we'll pick this up later when we make the connection to the Riemann hypothesis.